So in an AR1 process, if the row parameter is equal to 1, then we say that the AR1 process has a unit root. The presence of a unit root is really important because if the process has a unit root, we know that the stability condition must be violated, and then we know that the time series cannot be stationary. So it's important to try to figure out if your time series has a unit root. And that's the purpose of this lecture, to describe how to test for a unit root. So let's start with the simplest setup. That's the following. We have an AR1 process. Yt depends on a constant and its value in the previous period plus some error term, and we assume that the error terms are white noise. So remember, rho equal to 0, that will make this time series completely static. Yt will just be a white noise plus a constant. If rho is greater than 0, then we have correlation between Yt and Yt minus 1. If rho is between 0 and 1, strictly less than 1, then the stability condition is satisfied and the process may be stationary. However, rho equal to 1, we know that the stationarity cannot be satisfied. For the purpose of this lecture, let's exclude the possibility that rho is negative. It is very uncommon for Yt to depend negatively on its value in the previous period. Also, let's exclude rho greater than 1. That would imply that Yt was, let's say, 1.2 times Yt minus 1. So the whole process would explode really quickly towards infinity. So in this lecture, we only consider the possibility that rho is between 0 and 1, including 0 and including 1. The interesting case is when rho is equal to 1, then the process has a unit root. So now we want to formulate this as our null hypothesis. However, we are way more used to formulating hypotheses where we have a parameter being equal to 0. So let's first make a slight modification of the AR1 process such that we can write the null hypothesis in the form equal to 0. So what we do is we just look at the AR1 process in first differences. Here's the AR1 process. Let's just make a simple transformation subtracting Yt minus 1 from both sides. That will not, of course, change the relationship. So Yt minus 1 is beta 1 plus rho Yt minus 1 minus Yt minus 1 plus epsilon t. This part here, we call that delta Yt, the first difference in Yt. So we have this equal to beta 1 plus, I have rho Yt minus 1 minus Yt minus 1. So I can write that as rho minus 1 Yt minus 1 plus epsilon t. And I'm just introducing a new symbol. I'm going to call this delta. So delta is rho minus 1, or if you like, rho is delta plus 1. The point here, of course, is that rho is equal to 1 if and only if delta is equal to 0. So what we do when we want to test for the presence of a unit root, we rewrite the equation like this: beta 1 plus delta times Yt minus 1 plus epsilon t, and then we test the null hypothesis, delta equal to 0. So let's summarize this. We rewrite the AR1 process like this. The relationship between the variables are delta equal to rho minus 1. Since rho must be between 0 and 1, delta must be between minus 1 and 0. So we have moved the unit root from 1 to 0 in the sense that the process now has a unit root if delta is equal to 0. So formally, we set up this hypothesis, delta equal to 0, against fixing that to h1, delta less than 0. Note that when the null hypothesis is true, then the stability condition cannot hold. So if I reject the null, that means that the stability condition holds and it's possible for the process to be stationary. The following data is simulated from an AR1 process where rho is equal to 1, that is delta is equal to 0, and beta 1 is 0.1 in this case. Here is my first, and as we will see in a moment, unsuccessful way of testing the null hypothesis. So what we will do is we will simply estimate this rewritten AR1 process and simply test if delta is equal to 0 using a t-test. So in eViews you don't have to write yt minus 1. There is a shorthand command for delta yt, which is d parenthesis y. That's my y variable. I have an intercept c, and my explanatory variable is lag y. So like this, click OK. We can see that this is the estimated beta 1, pretty close to the true value, which is 0.1. And this is delta, which again is rho minus 1. So a straightforward way of testing for a unit root would simply be to look at this t-value or this p-value, and in this case we would not reject the null hypothesis, claiming that it's very possible for this process to have a unit root. Unfortunately, it doesn't really work, so we need to look at an alternative for the unit root test, which is called the Dickey-Fuller test. So if I estimate delta using OLS, it is actually going to be consistent. That is, there's actually no issues with this estimated parameter right here. However, there will be a big problem with this estimate. Under the null hypothesis, the data is not stationary. Due to the fact that the data is not stationary, implies that the standard errors will actually not be consistently estimated. It also implies that the t-statistic, this value right here, will not follow a t-distribution. When n is really large, the t-statistic tends to a normal distribution in the usual case. However, in this case, due to the fact that the data is non-stationary, the t-statistic will not be approximately normal even when n is very large. That means that to find the critical value, you cannot go to the normal or to the t-table. The p-values are calculated from the t-table, so those will be incorrect as well. So what Dickey-Fuller did in their famous paper was to figure out correct critical values. These critical values are sometimes called the Dickey-Fuller critical values. Fortunately, we don't have to go and look up these critical values. They are supplied in pretty much all econometric software. So this was a failed attempt testing for a unit root. A better way would be to use the Dickey-Fuller test. In eViews, it's very simple to do a Dickey-Fuller test. Just double click the variable, go to View, Unit Root Test. The test we will look at is the Augmented Dickey-Fuller test. I'll come back to in a second why it's called augmented. So we want to test for a unit root in levels. That is, we want to test if there is a unit root in our actual data. If you want to test if there's a unit root in the first difference of the data, then you click that one. But we want to do level. So what to include in the test equation? Well, the intercept. We have a simple AR1 process, and since beta 1 is not necessarily 0, we need to include that intercept. I'll come back to these two choices later. In this lecture, we have assumed that YT follows an AR1 process. So in that case, you need to click this one, user specified, and set this to 0. 0 corresponds to the AR1 case. And again, I'll come back to the lag length in a second. Click OK. So here is my augmented Dickey-Fuller unit root test for Y. First, you can see that right down here, it has done the same regression down here that we did over here using OLS. So that information is available. But again, this p-value is not correct. The correct p-values using Dickey-Fuller critical values are given over here. So here you can see, for example, the critical value at 5% level. The Dickey-Fuller critical values are in general much larger in an absolute sense. And this is the p-value. eViews also reminds you that the null hypothesis is the presence of a unit root. The humongous p-value tells us that we should not reject this. Of course, not rejecting doesn't mean that we have to accept that there is a unit root, but we can at least not claim that the stability condition is satisfied. So we should really work under the hypothesis that the data is non-stationary. Here I have the same data in Gretl. To do the Dickey-Fuller test, just go to variable, unit root test, augmented Dickey-Fuller. Lag order, we are doing an AR1, so we set that to 0. We only want to do the test with a constant, and we want to use levels. So OK, and the p-value for the test is right there, so that's the same as eViews. If you want to decode the information provided, it says that the unit root null hypothesis a equal to 1. So a, that is our row parameter. The model is 1 minus L times y. This L is the lag operator. So this part here, 1 minus L, is the same thing as taking the first difference. So the first difference in y is a constant, a minus 1, that's the row minus 1, so that's our delta, times lagged y plus some error term. The estimated value of a minus 1, well, that's the estimated value of the delta, precisely what we got in the eViews case. And finally, the p-value. Let's look at some versions of the Dickey-Fuller test. So far, this lecture has been based on the AR1 process, which gave us this specification by simply subtracting yt minus 1 on both sides. Delta equal to 0 is the presence of a unit root. There are a couple of things we can do. The first thing is that we can remove this intercept from the model. Your specification then becomes this. Now the thing is that the Dickey-Fuller critical values will be different if you don't have an intercept. So if you're working with an AR1 process without an intercept, you need to specify that in your software. Another thing one can do to this model is to add a trend to this process. So delta yt then also depends on time. We simply add beta 2 times t as an extra explanatory variable. The null hypothesis is still the same. Delta equal to 0 is the presence of a unit root. However, in this case, if we reject the null hypothesis here, claiming that delta is less than 0 or claiming that the row parameter is less than 1, the model would still not be stationary if beta 2 is different from 0, but it would be trend stationary. So this is a convenient specification if you try to determine if your data is trend stationary or different stationary. So that leads us to this model with a trend. If I reject the null hypothesis, delta equal to 0, and my estimate of beta 2 is significant, then it's trend stationary. If I reject the null and I can also claim that beta 2 is 0, then the process may be stationary. Finally, this model is really useful if yt follows an AR1 process. However, it's hard to know that 1 is the correct number for the AR process. So to safeguard for that, it's common to add to this model additional lags of delta yt. So we add, for example, row 1 delta yt minus 1. So we're not going to discuss the details, but a necessary condition for stability in such a model is still going to be delta equal to 0. But we're allowing for a more general specification for our time series data. You can of course add more than one lag of delta yt. So the general specification becomes this one. We've added delta yt minus 1 with the parameter rho1 going all the way to delta yt minus p with the parameter of rho p. The null hypothesis for a unit root is the same in all these cases, namely delta equal to 0. So it's quite common to call this test the augmented Dickey-Fuller test if you add these additional lags of delta yt. And it is possible also in this test to remove the intercept and or to add a time trend. So let's look at how to do these versions in eViews. Here is the unit root test where we have included a constant. Just make a note of the critical value in this case. So if I want to do the unit root test with no intercept, then I just simply click none here. And as you can see, that will change the critical values. So how are you to know whether you should include an intercept or not? Well, one idea you could get simply from the t-value of the intercept. If it seems like the intercept is significantly different from 0, as it is in this case, then include it. If you can remove it, that will improve the performance of the unit root test quite significantly. Adding a trend line, just click trend and intercept. You can see that the regression it has run is the first difference in y on lagged y, constant, and a trend. The critical values are even larger when you include a trend, decreasing the power quite significantly. Finally, to add lags of delta yt, you just specify here how many lags you want. So if you want one lag of delta yt, just do 1, and you can see that the model that's been estimated, well, in this case I also included a trend, you don't have to do that, but the model that's estimated is first difference in y on lagged y, first difference in lagged y, a constant, and a trend. The important parameter for the unit root test is always this one, if this one is significantly different from 0. But again, this p-value is not to be trusted. The p-value that we need to look at is this one. But we come to the same conclusion. Do not reject the null of a unit root, at least at the 5% significance level. Now, since it's difficult to know exactly how many lags to include, there is a way of making this selection automatic. I'm resetting this to just the intercept because I know that there is no trend. So I'm not going to cover exactly how this is done in this lecture. We click OK. Before I click OK, remember I've simulated the data from an AR1 process, so I actually know the correct value. The correct value is 0. I should have no additional lags on delta yt. Let's see what it finds. Well, it actually found that. It found the correct lag length, 0. So it has done a regression of first difference in y on lagged y and a constant. Gretl looks very similar. Just go to variable, unit root test, augmented Dickey-Fuller. Here you set how many lagged values of delta yt to include. Gretl can also do this automatically. So if I set this to 12, then it tests down and finds the optimal lag order. Here is the choice of what you want to do. If you want to do the test without the constant, with a constant, with a constant trend, and Gretl even has this choice of including a trend squared, which eViews doesn't have. So let's just do with the constant and see what the optimal lag length is according to Gretl. So that was pretty horrible. It actually includes 9 lags. The correct choice, of course, being 0. There are actually a lot of possible reasons for this. One is that the default criterion is the Akaike information criterion, while in eViews the default is SIC, the Schwartz information criterion. And I also think that they use a slightly different method. I think that eViews is testing up, that is, it starts with 0 lags and then add 1 lag to see if that improves the fit. If it does, it adds a second one. While I think that Gretl is testing down. So it starts with 12, checks if there's an improvement going from 12 to 11 and so on. In any case, the result is the same, however, namely that we should not reject the null.